So now that we've gone over the equilibrium properties of pure substances in the context of phase diagrams and also the Clausius-Clapeyron equation, what we do now is we switch gears, and because we're working towards chemical reactions and chemical reactivity, we start to talk about equilibrium properties of mixtures. Because before you have a reaction, you have to make a mixture, right? So what we're going to be discussing this video are just the basics of Raoult's law. So we're going to kind of give the Gen Chem version because you don't always kind of get this in general chemistry. And if you did see it before, it'll be a nice little review. Why I'm calling this the basics is because we're really not going to invoke any chemical potential arguments yet. We're literally just going to kind of look at the mechanics of Raoult's law, how it manifests, and different types of sort of algebraic analyses we can do with it. So here's the whole idea behind Raoult's law, okay? It ends up being a mathematical law, but I'm just going to kind of explain the physical ideas first. Vapor pressures, like those ones that we just were analyzing with the Clausius-Clapeyron equation, vapor pressures are modified by the presence of other particles. So let's kind of think about what vapor pressure is anyway. So we know that when we have these open systems, that there's a certain amount of kinetic energy that exists inside liquids. And that kinetic energy allows some of these liquid particles to escape into the gas phase, okay? So enough of these will go up and it'll follow that vapor pressure line, because this is a pure substance right here. It'll follow that vapor pressure line on the phase diagram, that liquid gas coexistence region, and these guys will enter the gaseous phase. Now, because you're not boiling and you're just evaporating, or just vaporization is occurring, the atmosphere is pressing down with all its particles and it keeps these guys kind of close. So keeping these guys kind of close means that they're free to also come back down. So an equilibrium is established in a pure substance, and then there's a certain amount of particles here. So that means there's a certain amount of pressure that's made from the particles that actually escape into the gas phase. And again, it makes sense if you follow like that vapor pressure curve. We know that as we increase temperature, vapor pressure goes up because we're adding more kinetic energy, which means that we're making more of these go into that gaseous phase. And then more particles in that gaseous phase means more vapor pressure. So what happens when we have a mixture? So let's talk about, just putting anything in there. Let's start with something that's not going to itself evaporate, like say like an ionic solid that dissociates into ions. It itself is not volatile, but it's going to be distributed throughout the mixture. So now, right, what ends up happening, and we'll talk about why in a second, as you put other particles in there, P-vap goes down. So you had a pure vapor pressure, you throw other particles in there, and the vapor pressure goes down. The reasoning for that is now, for a particle to get up into this vapor phase, it has to get close to this surface, okay? A particle that's way down here would start to work its way up to the surface, and if there was nothing in its way, it could get up and make that vapor pressure. But we can see with this particle, there's actually now another particle in the way, right? Just to reiterate that, this guy's trying to make its way to his surface to actually get up into that phase. Well, now it's blocked. It's physically blocked by the presence of other particles. There's also these particles on the surface. These are more important ones. Those definitely block, all right, these particles from getting to the surface. If they can't get to the surface, they can't enter the gas phase, and so P-vap goes down. Also, as soon as you put in another particle here, right, it's not just that they physically block, all right, the other particles from getting to the gas phase. They also could interact with these particles. Maybe there's a strong interaction there. It's trying to look like a double arrow. Sorry. Maybe there's a strong interaction here between particles that prevents this from working its way to the surface, right? So for those two important reasons, the physically blocking of the particles from reaching the surface and also the presence of other molecular interactions, what happens is P-vap goes down in general, right? So then what was known, or what was observed empirically by Raoult, is if you kind of look at what happens, P-vap is going to go down, but it goes down in a proportional way. So P-vap we're just going to start labeling as P, because just for this whole section we're talking about vapor pressures. So the vapor pressure, right, that you see actually looks like the mole fraction, right, of the particle you're trying to analyze in solution, the mole fraction in solution, all right, times the pure vapor pressure. right? The pure vapor pressure. Now, how this makes sense, okay, so this is the vapor pressure in the solution, right? And it's gone down proportional to its mole fraction, right? This is the vapor pressure that we had before when we just had blue stuff. This is the pure vapor pressure. So this chi is mole fraction. Why does this make sense? Chi is mole fraction. It looks like moles of a part over the total moles. So it has a range. It could go from 0 to 1 essentially, okay? And if I'm looking at the vapor pressure of this blue thing, right? If chi is 0, there are no moles of it in there, so it doesn't have a vapor pressure. That makes sense. If chi is 1, then the vapor pressure you observe is the pure vapor pressure, which also makes sense because if chi is 1, then there's only one species in there. N total is N of that part, right? And just in case this isn't clear, this is something that you should know. I think we talked about it before, even in our class, but definitely from general chemistry. N total is just going to be like you sum up all the moles of the species in there. So if this is 1, that means there's only one species in there, and it looks like you're getting your pure vapor pressure, and that makes sense, right? So this is Raoult's law, but now it's kind of an empirical thing, but it's an empirical thing related to, right, a certain type of solution, right? Raoult's law is applicable for ideal solutions. So it's an experimental observation that works for these solutions that we're going to call ideal. Ideal solutions are not ideal gases, right? We're talking about a mixture of liquids here. We're mixing two liquids together. So what is an ideal solution? When can we assume that Raoult's law is applicable? It's all about molecular interactions from the basic level. So essentially what you have when you put two liquids together or you dissolve something in another liquid is you have a solute and solvent. So there's 3 different interactions that occur when you make the mixture. The solute particles can interact with other solute particles. The solvent particles can interact with other solvent particles. And then there's the mixture interaction where a solvent particle could bump into a solute particle and interact with it, right? Ideal solutions from the basic standpoint, all right? All of these must be equal for you to have an ideal solution. So you have to go through your general chemistry work and say, okay, solute interactions, solvent interactions, and solvent-solute interactions, they're all the same. Then you have an ideal solution and Raoult's law is applicable, okay? Just a quick little example of an ideal solution. I mean, think about non-polar things mixing together, right? I think your book says like this example. So what about like C6H6, like benzene? And I mean, anything really. C8H18. Oh, not aqueous, sorry. Let's mix these two liquids together. If I want to decide whether this is going to make an ideal solution or not, let's just take this and pretend it's our solute, okay? So what are these interactions going to be? Well, the way that two non-polar things interact, C6H6, how does it interact with a C6H6? They interact with van der Waals interactions or induced interactions. I won't abbreviate this. Induced dipole to induced dipole interactions. You actually have to make the dipole form to be able to observe any sort of really strong interaction. And remember, induced dipoles are short-lived and weak interactions, right? How does a C8H18, which again just contains carbons and hydrogens, so is definitely going to be something that's non-polar. When this bumps into itself in your mixture, what do you see? You see the same interactions, induced dipole. Wait, C6H6 is nonpolar. C8H18 is nonpolar. Nonpolar things always interact in the same way. All right, all of these are the same, so we assume that this is going to make a ideal solution, so Raoult's law will be followed, right? As soon as you have a situation where any one of these is different, then you're going to have issues, right? So let's take C6H6 and CH3OH. For something like methanol, it definitely has a non-polar part, but it also has a polar part. And if you remember the structure over here, it kind of looks like water with a CH3 hanging off of it. So this oxygen definitely has a dipole. Well, wait a second. We know the interactions that are going to happen inside here. We're going to get just induced interactions. Over here, we're going to get induced interactions, sure, but in a pure sample of this, we're also going to get hydrogen bonding. When I put these guys together, all right, the C6H6 by itself, it only ever has these induced dipole interactions. When these guys interact, yep, if the non-polar things bump into each other, you're going to get induced dipole interactions. But what happens when, all right, the polar part of CH3OH touches the non-polar whole entire C6H6 molecule? When those things interact, you're going to get an induced dipole to permanent dipole interaction. An induced dipole to permanent dipole interaction. And for those looking at these interactions for this sort of thing, new interactions have been introduced here that weren't present in this. All the interactions are not equal. And so what we end up with is a situation where this is a non-ideal solution and Raoult's law will not be applicable. So it's all about being able to do that general chemistry work and deciding what the interactions are. They have to all be the same for you to be able to assume that you have an ideal solution. All right. So what happens when you don't have an ideal solution? Well, Raoult's law will not be applicable, but what we're going to get are deviations from this Raoult's law standard that we're starting to describe. And if you look at the interactions that are involved and you've introduced a repulsive interaction, just like that last example, non-polar things and polar things, they don't like to be near each other. If you introduce a repulsive interaction when you make the mixture, then what we're going to say is that we have a positive deviation from Raoult's law, and that Raoult's law prediction is actually not enough in terms of predicting what the vapor pressure is, because the repulsive interaction actually pushes, it pushes more particles than is predicted by Raoult's law. It pushes more particles into the vapor phase. Sometimes you'll look at the interactions and you'll see that an attractive interaction shows up that wasn't there before. And this often happens when you have like a hydrogen bond that's not possible until you make a mixture, right? For one of the species has a permanent dipole, but then you can throw it into a situation where it gets a hydrogen bond. Well, now an attractive interaction has been introduced. So for these sorts of situations, we actually get less particles into the vapor phase than Raoult's law predicts, and we call that a negative deviation from Raoult's law. All right, a negative deviation from Raoult's law. And again, the reason that you have this negative deviation is there's more hold on the particles than you would have an ideal solution, so that equals less escape of particles into the vapor phase, which means that P is going to go down, that vapor pressure goes down, okay? So these are the two sorts of deviations that we'll see. It's really actually hard to make an ideal solution, but Raoult's law is our standard for what an ideal solution is. So it's important to know when we'll have it and when we won't have it, and whether we're going to see more vapor pressure because of a repulsive interaction that was introduced, or less vapor pressure because of an attractive interaction that was induced or introduced. So let's take a look at Raoult's law plots for binary situations or for binary solutions. All right. Now, for binary solutions, and let's just say that we have two volatile components, because these are most of the solutions that we analyze in this chapter. All the ideas behind Raoult's law still applies. I'm just going to make this picture one more time to make sure you understand. So, here's our vapor pressure picture. We have some blue particles in here that are volatile. So some of them near the surface are moving up into the gaseous phase, and there's going to be an equilibrium that's established. But inside here, we also have red particles. Okay? And so these are volatile now this time. Some of these are volatile. And so the ones near the surface can escape into the gaseous phase. So up here, what we do with Raoult's law is we assume that we have an ideal gas of vapor pressures, right? So we know that up inside here, we're going to have a situation where the total vapor pressure up inside here is the pressure from the blue plus the pressure from the red. And I'm just using like the subscript of the dot. So this means pressure of the blue dot plus pressure of the red dot. Well, hold on a second. I know what each one of these individual vapor pressures are because I can use the same arguments over here to decide what happens because now they're solute there. Well, if you look at what the red does to the blue, does it block from the surface? Yeah. Could it interact, right? Or could it make interactions between these particles that sort of influence how it affects going into the vapor phase? Well, yeah. So relative, right, to the blue, the red does everything that we said before that prevents it from getting the surface, and so PVAP is lowered. So let's assume it's an ideal solution. Then this guy right here, we know what P dot is. This total vapor pressure that we have for the solution, this would be chi for that species, and I'm just going to call this species 1, and P star for that species, right? Now that looks like what we had before, but we notice that there's this red dot now there too. That's also trying to escape into the gaseous phase. That's also blocked from the surface due to the presence of other particles there. That's also possibly interacting with other particles that are present in the surface. So the same ideas follow for how the red behavior would be noted in the context of ideal behavior. And so what we get here from the standpoint of a total vapor pressure of your solution now, when you have two volatile components, is it looks like I apply Raoult's law for that guy, and I apply Raoult's law for that guy, and this is my total vapor pressure formula that we're going to analyze in the context of Raoult's law. So this is a little bit more complicated than just having one volatile component, but it's not completely more complicated because we use the same arguments now to create our equation. So Raoult's law graphs end up being really important. And I'm just going to rewrite this equation at the top because we'll be able to find the information there. So P tot. We'll be able to find the information from the equation in the graph as always. Chi1 P1 star plus Chi2 P2 star. For a binary liquid, that's ideal. This will always be the equation that we can use to analyze the total vapor pressure. Okay, so here's what a Raoult's law plot looks like. It actually kind of looks like a box. And you'll see this in your reading. Okay. Your reading might not actually give it like a box, but I like to kind of think about it like a box. Okay. What you do is you pick an axis here that you're going to have one of the mole fractions in. All right, so let's say that this is Chi1. Then up here, we can write Chi2. Now, why is that? If you remember how Chi1 and Chi2 relate to each other, they're the only two components in the solution. And remember that those are referencing to the mole fractions inside the solution. Well, if there's only N1 and N2 inside that solution, and Chi1 goes from 0 to 1, right, as its max value, then what's Chi2 doing at the same time? Well, Chi2 must be going in the opposite direction. As you increase the mole fraction of one species, you automatically decrease the mole fraction of another species. Okay? So it's this idea that chi1 plus chi2 must be equal to 1. You should be able to make sense of that based off the mole definitions in chi, right? That we get to use here to make this box-like graph, right? So then over here, we can look and we could say, well, wait a second. When chi1 is 1, what do we have? We have pure 1. And what we're going to put on this axis is pressure, okay? And we're going to show which pressures are which. But when I have pure 1, okay, right here, this value that's measuring pressure, this is P1 star, right? Now, what this says is that these guys are proportional to each other. There's a proportionality here, chi1 and P1 star. The linear behavior for that vapor pressure for component 1 looks like this. There's that direct relationship. There's that linear behavior, right? All this line is saying is how we created this, that when I'm talking about the pressure for component 1, right, it looks like chi1 P1 star, right? That looks like a proportionality. It looks like this line, okay? Now what about P2? Let's say, for instance, that P2 has a lower vapor pressure just for the sake of it. It doesn't always have to. Let's see what happens if I go from chi2 equals 0. Oh yeah, chi2 equals 0. That's pure 1. Makes perfect sense. So I take pure 1 and I go in this direction, and the 1 goes away and the 2 starts to be made. Over here, if this is measuring pressure, this is P2 star, okay? If I look at P2 by itself, right, this looks like chi2 P2 star. It looks like there's a proportionality constant there, right? Up here, please note that this looks like the vapor pressure for component 1 plus the vapor pressure for component 2. I know we went over that already, but it's kind of nice to see in equation form, right? So what does this look like? It looks like another proportionality, but now the thing that you have to realize is the axis is actually going this way. So when I have pure component 2, I see that I have the pure vapor pressure actually recovered. The total vapor pressure I'm going to write in green. The total vapor pressure says wherever you are in terms of your chi's. So I construct a solution. And when I construct a solution, say I have a chi1 that's 0.3. Let's say I have this solution, all right? Automatically, since I know that chi1 is 0.3, I know that chi2 is 0.7 because these two guys, based off their definition, have to add to 1. Now, what I'm asking with this equation and what this graph will show is for all the series of possible chi1s and chi2s, what's the total vapor pressure? Well, the total vapor pressure says what you do is you find your vapor pressure for component 1, you add it to the vapor pressure for component 2, and what you get is the vapor pressure at that point, okay? That's the total vapor pressure, P1 plus P2. So if you do that across this whole entire way, what you'll see is what ends up happening is you get this total vapor pressure that looks like this, okay? So this right here, this is our P tot line. That's our total vapor pressure line, all right? Hopefully some of this is familiar. Now this applies for ideal solutions, okay? So be able to dissect this, right, and kind of understand what it means. But this is the total vapor pressure right here, this point. For this fictional solution that I made, that's 0.3 mole fraction of 1 and 0.7 mole fraction of component 2, okay? That's going to be the total vapor pressure right there. If I have another solution where it's 0.7 of chi1 and 0.3 of chi2, my vapor pressure would be there. That's how you kind of use these graphs, okay? So hopefully that's clear, make sure I understand it. Now, let's talk about deviations. So this equation is the equation that you'll use to make these predictions about total vapor pressure for these binary systems. So what happens when you look experimentally at what's actually happening with vapor pressure and you see an actual experimental line that does something like this? Is that following the predictions of Raoult's law? And the answer is no, right? It's not following what the Raoult's law prediction for ideal solutions is indicating the vapor pressure should be. And in fact, you have more vapor pressure than you would expect via Raoult's law. So what does this indicate from our previous discussions? This is where we're going to have our positive deviations. So inside that mixture, what you must have is you must have these repulsive interactions occurring that push more vapor into the vapor phase than you would expect for an ideal solution. That's what a positive deviation looks like. So what does a negative deviation look like? So we do this Raoult's law prediction. The green line predicts what the total vapor pressure should be for all these different solutions that we make for different Chi1s and Chi2s. And then this is what you see instead. All right. This right here, this line that we're showing here, this bottom black line, what happens is, it's below, all right, that line predicted with Raoult's law and assuming ideal behavior. And so this line below the green line, this is obviously our negative deviation. So if there's some sort of attractive forces that get put into play, all right, then we know that, okay, what we have is a situation where less gas is escaping, so you see a smaller vapor pressure. Right? You'll see both types of graphs in your book, and I'll point them out in your reading assignment, but it's really kind of important and interesting to understand where this is coming from. Ideal behavior is going to be when this is valid, and when we get something experimentally that's different, it's either going to be because there's positive deviations or negative deviations to Raoult's law. Okay? So what types of math problems are you going to see? You're going to see problems where you have to use Raoult's law like you did in general chemistry, or maybe you didn't get to use it in general chemistry. You'll have to use this equation essentially. The hardest types of, okay, so then the other things that you have to realize is these are often coming from experiments, and then the only thing you kind of have to remember is that Chi1 and Chi2 relate to each other, okay? So if it ever looks like you're just given one of these Chi's, just always remember that Chi1 plus Chi2 is equal to 1. So if I ever give you just one of these, you know what the other one is, all right? You could be given a total vapor pressure. It's essentially an equation with 5 unknowns, and you have to figure out what 4 of them are with these 2 equations. Not too bad. Where it gets a little bit more complicated is when you get questions about the mole fraction in the vapor. Which is different than the mole fraction in solution. So the Chi's we use for mole fraction in solution, right? The moles of the part over the moles total in solution. That doesn't translate to the same mole fraction in the vapor. And so what we're assuming here when we're doing these calculations is that we have not only an ideal solution, so that Raoult's law is applicable, but that we also have an ideal gas. And I'll remind you Dalton's law of partial pressure one more time, is that P total then is equal to the sum of both components, all right? P1 plus P2. We can kind of see that up here, but, all right, how does mole fraction in the gas phase, what's that other part of Dalton's law of partial pressures that matters? I'm going to call the mole fraction in the gas phase Y, all right? So the mole fraction in the gas phase for a component, if you remember from general chemistry, it looks like you take that partial pressure, the pressure from that one part, and you divide it by the total pressure, okay? So sometimes this is an extra step that has to occur. You get all this information up here, and then they ask you to calculate the mole fraction, not in the solution, but in the vapor phase. So for example, with just this setup here, what was Y1 equal? Well, if I look at what P1 is, P1 over P tot, okay? P1 is Chi1 P1 star. And P tot is Chi1 P1 star plus Chi2 P2 star. Okay? So it's an extra step that sometimes happens at the end of a problem that you have to analyze it from this context. Okay? Making the same connections that you did in general chemistry. Right? If I did Y2, what changes? Well, remember this is a general formula where that's the only subscript that changes. So this would be P2 over P tot. P tot remains the same, but then this is going to be Chi2 P2, the mole fraction in solution, and then the mole fraction of that component as if it was pure. Again, When you do these, you're going to be assuming that you not only have ideal solutions so that this is applicable, but that you have an ideal vapor that you've made. You make an ideal gas vapor. So this leads to a bunch of problems that you can do. It's all good stuff to know. It's great connections to things that you've learned in general chemistry. What we're going to talk about next time is ramping it up a bit and now coming back with our equilibrium ideas, coming back with chemical potential and analyzing these systems now from the standpoint of what thermodynamics information can we pull from an ideal solution and what happens if it's not ideal. How do we deal with that from a mathematical standpoint?